Good day to everyone. I'm happy to be a keynote speaker of this conference. I appreciate the organizer for the invite, and I also welcome everyone listening to this particular presentation. Based on the invite, I've been given 10 to 15 minutes to speak. I will try as much as possible to maximize the time. In order not to waste more time, let me start. So I'll be giving a keynote on the topic titled Artificial Intelligence and Machine Learning Approaches to Computational Electromagnetics vis-a-vis Antenna Array. Outline of my presentation: I'm going to give a general introduction. Two of my previous works will be presented. Future research directions will be given. Conclusion will be given, and there will be time for question and answer. The basics of machine learning are known to virtually everybody in different fields of studies, not only in communication or engineering. The techniques are being applied in several other areas of professions. So we have an overview. The slide 4 talks about the overview of machine learning techniques in direction finding. Direction finding is actually important in monitoring, tracking, and positioning of our system. So the breakdown or the little overview is given in this slide 4. There are different algorithms that have been proposed in the past, and we have the SVC algorithm, we have the backpropagation NN, we have deep NN, we have PNN, we have a whole lot of them. So a machine learning algorithm takes in an input and give an output. So we all know that the machine learning algorithm, they are data hungry. They require data for us to be able to have a model that we can trust. Now, in S parameter, as I've said, that the machine learning can be applied in different stages of computational electromagnetics: at the design stage, in the computational stage, even in the deployment stage. These techniques can be applied. Now, the use of neural network for the simulation of some basic, maybe filters, antenna, and other stuff, they are currently in vogue, and a lot of companies are actually working on this to come up with more robust environment where simulation design and other stuff can be done. Now we have another stage, a way to demonstrate how a predictive network of metamaterial with split ring resonator based on deep learning. We have generally a machine learning module takes in input to give an output. So in this case, we have the wavelength being an input to also get wavelength as output, but then of different input when we are testing and training. When we are training, we can train with a set of data, but when we are testing, we cannot test with the same data. We need to test with another data. So this technique has also been applied in path loss prediction. Path loss prediction have been the principle of machine learning have been applied to path loss prediction. Path loss prediction in communication link is important for in planning and link budgetary. So this gives us a profile of how the losses to expect. So this is usually done in broadcasting, in different networking and other areas. So I'll give an overview of two of my previous work that I did recently. One has been published last year. The other one is newly accepted. The first one reads an intelligent deep learning-based direction of arrival estimation scheme using spherical antenna array with unknown mutual coupling. That was published in IEEE Access. Now, why spherical array? Spherical array are generally being used in spacecraft and satellite communication. Why? Because they give they have isotropic characteristics which is needed for such application. Now, the signal model here is given here as the equation 13 here. But for detailed analysis, I enjoy everyone to visit to download this particular paper. If there is any problem or something that you don't understand, you can reach out to me either by email or by call or whichever way, then we can discuss better. Now, feature extraction, because for us to know the feature that we're going to use to estimate the elevation and the azimuth, we need to first of all get the feature of the spherical harmonic, which is in terms of magnitude and phase, or the combination of the two. So, the deep neural network scheme for DOA are using spherical harmonic feature as input is what is we are actually doing. But there is a problem because the spherical harmonic features is affected by noise and reflection. But then we are still able to get a good training method for us to have our model. The architecture of the CNN is used is this, and the definition of each term is as presented. Now, the feature DOA estimation with CNN. So the feature extraction of the P and the M feature can be extracted under the classes of the azimuth, and the P, the phase feature can be extracted under the classes of the azimuth. So, and these are used as our training data for our network. So the proposed procedure for DOA estimation and mutual coupling calibration is here, and we all see, and we equally investigated the existing algorithm, how they can be used to reduce mutual coupling problem. And this is a proposed algorithm for DOA and mutual coupling calibration. Furthermore, we work on the experimental data which was taken in an anechoic chamber using an already designed spherical antenna array to measure DOA at different angle within the chamber. So more experimental architecture the explanation at the architecture of the experiment is can be given in the given in the paper. So here are some of the result comparison between our methods and previous methods. So we also demonstrated performance evaluation using gross error performance of all the methods compared with some method. We can see that our methods perform so well. Also, we consider the performance for sparse DOA search and search grid and dense DOA search grid. So you can see in both under both conditions that the method, the AI-based method, performs better than the existing method. So we also try to analyze the complexity of this method compared to the other methods. We can see that in both sparse and the dense in sparse domain and dense domain, we can see that the CNN-based approach perform better than the music-based approach. So we applied this method for using. We also extended the application of this method to mutual coupling calibration, and we applied a spatial spectrum profile, and we compare it with that of our method. We can see that our method has a sharp edge, which is expected, and that shows that it can also be used to mitigate mutual coupling. And this is the DOA estimate against the SNR compared to the two algorithm that were employed for previous works, and we can see the performance of our algorithm, that is not the worst and it's not the best, so it's fall within. So it shows that it can really be adapted. Furthermore, I would like to present the second paper, which is recently accepted in ICT Express, ICR. So it is about electromagnetic machine learning for estimation and mitigation of mutual coupling in strongly coupled arrays. So we have the mutual coupling problem has been in existence for years, and there are a lot of work that have been done to reduce this problem. I employ a method to be able to quantify and characterize electromagnetic wave, an incoming electromagnetic wave, for me to generate a deviated voltage that is being coming before applying, before feeding into the machine learning module and get the optimized machine learning, or the optimized voltage, which is the core, the direction of this work. This is the architecture, this is the proposed architecture of the work in this slide 32, and we can see that this is the incoming, the EM in the EM interface and the DSP interface. We have the EM interface where the incident EM comes in, and the ACGL is applied for us to be able to separate them and have for one, depending on the number of elements we have in the array, and each of them will generate a deviated voltage, which is also labeled as 1. Like F1 will generate V1, F2 will generate V2, and then the optimizer, after applying the machine learning module to it, will get our optimized voltage. So the whole of this process here, from this input voltage to output voltage, is what I propose to be a DSP module for circuit designer, that if they can make this can be used to actually correct the mutual coupling problem we have in strongly coupled array in microwave systems. So this is the procedure. The procedure for the implementation of the algorithm is given here. Now we verify the potency of this work by using a uniform linear dipole array of half wave wavelength on x-axis. We simulated this using HFSS, and the data were used for the analysis. So we estimated the behavior of the model using single and double sources. For single source, we can see the performance that our proposed method share close relationship with the ID behavior, while in two sources case, it's also share same profile with the ID behavior. So which makes it to be a good option or a good technology for our systems. And the same thing is also done here at shorter wavelength, which makes it that when the problem becomes more in the mutual coupling effect, so this is the performance. And we also compare the method with conventional method in terms of mutual coupling, and we see that this is the spatial spectrum profile that we fed into the system, and this is the comparison. You can see that this is a good behavior or profile, and then we can see the result, the MMSC of the DOA against the XNR. As we can see that our result perform better than the mutual coupling low spatial smoothing algorithm, but then share close profile or behavior with blind calibration spatial smoothing algorithm. We plotted the training accuracy and testing accuracy, that is the plot of accuracy versus the epoch. So this describes the efficiency of our work. Now, based on what I've said so far, we have a lot of work to be done in the future, which I also invite everyone to look into this using the same machine learning or artificial intelligence algorithm to solve this problem in terms of beam steering, antenna design, metal surface and metal materials, propagation, array processing, mutual coupling in arrays, and many more. In conclusion, we have proposed a uniform MML framework for estimation and computation of mutual coupling in receive mode antenna arrays. 2. ACGL formalism was employed to adequately characterize electromagnetic response of radiators in form of DSP module with the inclusion of mutual coupling effect among the elements. We have proposed a robust DOA estimation and mutual coupling compensation technique based on CNN for spherical array. Spherical harmonic decomposition is used to facilitate feature extraction in two sets, which contains different features about the elevation and azimuth of the source for DOA estimation. To solve the MC error, the mutual coupling error, the DOA estimation scheme is also used to obtain accurate spectrum peak in the multipath scenario with unknown mutual coupling and sharper spectrum peak via the unique structure of the mutual coupling matrix and spatial smoothing algorithm. These are the selected references. I refer all my listeners to the first and the second, which are the papers, which are the works I just presented here. And in case there is any question, you can always contact me. Thank you once again for the opportunity. Thank you for listening to me. Thank you, and God bless you all. Thanks.